Hello, this is Lisa Seidman, and this is video 6 in a series of videos dealing with calculations relating to preparing laboratory solutions. This final video in the series discusses multi-component solutions, that is, solutions that contain more than one solute combined together in water. So this is the 6th in this series. These previous videos introduce things like amount and concentration and different ways in which concentration can be expressed, such as a simple ratio, a percent, molarity, and millimolarity. So let's move on now to multi-component solutions. But first we're going to take a quick stop in the kitchen, and we're going to make some apple crisp. So this is a very typical recipe, and you can notice that it has some components. There are the components of the recipe are the components of apple crisp: rolled oats, honey, flour, butter, cinnamon. And the other thing right here is that this recipe tells us how much of each we need. So we need 3 cups of rolled oats, a half a cup of honey, a cup of flour, and so on. Another thing we'll note about this recipe in the kitchen is that it tells us what to do with these components. So we're going to take them, we put the apples in the bottom of the pan, crumble the oat mixture, and so on. So it has 3 parts. It's telling us the components of apple crisp, how much of each component we need, and what we do with those components. Okay, now let's take a look at a laboratory recipe. So this is like a recipe for making a solution. And again, we see the components. There are 4 components: sodium phosphate, potassium phosphate, sodium chloride, and ammonium chloride. And this is a fairly simple recipe which gives us how much of each: 6 grams of this one, 3 grams of that, 0.5, and 1 gram. And as in the kitchen recipe, there are some instructions for what to do. You dissolve it, you dissolve these components, you bring them to a volume of 1 liter. This is the simplest way in which we might see a recipe expressed. But when we go into the professional biotechnology literature, it doesn't look quite like that. So we've looked at RepaBuffer several times in past videos. So reading this again, it says cells were lysed on ice with cold RepaBuffer, and then parentheses, and it tells us the recipe for RepaBuffer. But it's a very shorthand way to tell us. It has 5 components: sodium chloride, tris, NP40, sodium deoxycholate, and SDS. But it does not tell us, this recipe here, how much of each. We don't see anywhere, so how many grams of sodium chloride or tris or NP40? It doesn't tell us. What it does tell us is the concentration. So millimolar, that's a concentration. Here, millimolar tris. Here, 1%, remember that's a concentration, 0.1%, and so on. The other thing that's missing here are instructions for what we do with these components. How do we combine them? What do we do with them? The author of this recipe assumes that you know how to interpret these concentrations and that you know what to do with these components. So let's think about that. But in order to get there, before we think about REPA, we're going to start with SM buffer, another common molecular biology buffer. Here, I've listed the ingredients instead of putting them in parentheses with commas, so they're a little easier to see. So there are 4 components in this buffer: 2/10 molar tris, pH 7.5, and we'll talk about that in a minute, 1 millimolar magnesium sulfate, etc. So here we have 4 components. What do we do to make our solution? Now, the first thing people sometimes think about doing is to get 4 bottles, and they make up each of these components to whatever concentration they're supposed to be. So maybe they make up 2/10 molar tris here, 2/10 molar tris, and they make up some magnesium sulfate here to the final concentration, and so on. And then they think, okay, then I'm going to combine these together to make one solution, because it is supposed to be one solution. And that's not going to work, because if you make these to the final concentration that you want, and then you mix them together, they're going to dilute one another. So you will no longer have the right concentrations. So that strategy, which sometimes people instinctively want to do, is not going to work. So what might work? Well, the first thing we're going to do is we're going to decide how much volume to make. So remember, the recipe did not tell us that, because the author didn't know how much we want. We're going to make a liter, but maybe we want 100 mils. Somebody else might want 10 liters or 100 liters. The author doesn't know how much you want, so you have to figure out how much you want. Okay, so we're going to talk about the tris. Okay, so first of all, we're going to go into our storage cabinet. We're going to find our tris, and we're going to discover that its formula weight, how many grams are there in 1 mole, is 121.1, or sometimes we'll use 121.14, but let's use grams. We'll use 121.1 per mole. Now the molarity that we want, which was in our recipe, was 0.2 moles per liter. And we said we're going to make a liter. So our units are going to cancel. And if you do the arithmetic here, you'll wind up with 24.22 grams. So that's how much we're going to weigh out. So then what do we do with that? Okay, well, we go to our lab, we weigh it out, and we dissolve it in water. We dissolve that powder in water, but not the full liter that we want, only 700 mils at this point. The other thing we're going to note here is that this pH needs to be 7.5. Some people would, at this point, bring this solution to 7.5. You actually add HCl, but we're not talking about that in detail in this video. Other people might bring it to that pH after they've combined all of the reagents, all the components together. But again, that's not exactly the topic of this video. So at some point, you would bring this to pH 7.5. So now we have a beaker. The tris is sitting in this beaker. It's spinning around and around to get it dissolved. And then we go to our next component. So magnesium sulfate is the next component. We want 1 millimolar. Now I want to make a point about the magnesium sulfate. Magnesium sulfate comes in more than one form. This might be anhydrous, but when you go into your cabinet, your chemical storage cabinet, you might discover that you don't have this form of magnesium sulfate. You have magnesium sulfate with bound waters. So for example, 7 bound waters. That might be the formula it shows on your chemical reagent. That's fine. These waters are bound to the magnesium sulfate crystals. They do not make the magnesium sulfate into a liquid. They don't make it watery. It's still a powder. It still looks just like any other powder. But there is water bound to it, and so the formula weight reflects that water. This formula weight is for this form of magnesium sulfate. You can use other forms. You could use anhydrous, you could use magnesium sulfate with different numbers of bound waters, but you need to pay attention to which one you have. That's why it's really important to look on the reagent bottle for the formula weight of the reagent that you have in hand. Okay, so now that we know that, we can plug into our handy-dandy formula. So we have 246.5, and this time I'm going to not show you the units, but they are there, times the molarity. Now remember, 1 millimolar is the same as 0.001 molar. It's very important that our units be molar, not millimolar, times 1 liter. And that, if you do that arithmetic, you are going to come out with 0.2465, and these are grams. Our units are grams. So that's how much we would want of the magnesium sulfate. And what do we do with it? Well, we take the magnesium sulfate, here's our magnesium sulfate, and we add it into the tris buffer. So the tris buffer is already sitting here. We add it in to the tris buffer. All right, now we can go to our next component, which is sodium chloride. Formula weight, 58.44. How much of it do we want? Well, we want 1/10 molar. So again, we can plug into our handy-dandy formula, 58.44 times 0.1 times 1, and we get 5.844, and grams are the units. So again, we weigh it out, we add it into this container that has our other components. Okay, fine. Now what? Okay, now we want gelatin. And we might think, okay, we need to find the formula weight, which by the way is variable, it depends on the gelatin you have. But it doesn't matter because look, the gelatin is expressed in terms of percent. Remember from previous videos that when you have a percent solution, you don't need to know the formula weight. What you need to remember is that 0.01% means, by definition, 0.1 grams per 100 mils. Now note, it didn't have the little weight per volume thing here in the recipe. But if you go into your cabinet and you find that it's a powder, which in this case it will be, that it's going to be a W/V, weight per volume. 0.1 grams per 100 mils, by definition, is what this means. But we don't want 100 mils. We want 1,000 mils. So, how much gelatin do we want? Well, again, we can go ahead and we can solve this, and we get that we want 0.1 grams of the gelatin. So now what we do, we take our gelatin, weigh it out, and we dissolve it with the other components. So now they're all sitting around in here. Now we have a little bit more than 700 mils, stirring around and around. And then finally, our last step is to bring it to volume. We could use a volumetric flask, as is shown here. We could also use a graduated cylinder. Either way will work, but we bring it to 1 liter, and we have our final solution. So this is our final solution, a multi-component solution of SM buffer. All right. Now let's go back to REPA buffer. At this point, I want to make a few points about this buffer. First of all, this was what it said. Cells were lysed on ice with cold REPA buffer. So if you were trying to repeat what these people did in this article, in this scientific article, you would want to make this solution like they did it. Now, it's very important with lysis, with any buffer, but lysis buffers, their purpose is to break open the cells, to release the components of the cells so that you can get whatever you're looking for. Maybe you're working with DNA, RNA, proteins. It's important that you make this buffer consistently and correctly, because depending on the exact formulation you use, you might get slightly different things being released from your cells. And there are indeed different recipes for REPA buffer. It's not just one thing. It is always some sort of a buffer. There's usually sodium chloride, and there are detergents which break open the membranes. But the exact formulations can vary. So you want to optimize it for your system. So if you're following this particular recipe, you want to make it exactly correctly and exactly the same way each time. And I'm just going to point out here that I'm not going to talk about the NP40 in this particular case. This is a little bit more tricky, so we're just going to ignore it for our purposes right now. Okay, so how do you do it? So my suggestion here is, why don't you pause the video for a few seconds, and why don't you take a look at this and try to do it on your own. Here's some formula weights for you, because I looked at the chemical bottles to find out what they are. And pause the video and then come back in a few seconds and we'll take a look at this. Okay, let's start out. And in this particular case, I'm going to start out with the sodium chloride. But you might have started out with the tris or one of the other components, and that would be perfectly fine. So again, the sodium chloride, we want 150 millimolar. So what are we going to do? Well, we're going to use our usual formula, 58.44 times, now we have to divide this by 1,000 because it's millimolar and we want molar. So this is going to be 0.150 times, and let's make a liter. I didn't say that before, but I think that will make this calculation simplest. If you did not choose a liter, then you're going to you can adjust your calculations for that. And if you do this calculation, you're going to come up with 8.766. And remember, that's the number of grams that you want of sodium chloride. So as before, you're going to put this into some water, less than a liter, say 700 mils like we did before. You're going to dissolve it. It's going to be sitting here in the water, stirring round and around while you prepare the other reagents that go in. So then let's go to the tris. All right, so the tris will use 121, and in this case I gave you 121.14 as the formula weight, times the molarity that we want, 0.025, and in this case I'm making 1 liter. So if we do the arithmetic, we get 3.0285 grams. So that's how much tris you want. That's a 3 there, 3.0285 grams. So again, we go back to our beaker where we already have some of the sodium chloride stirring around. We add this into our beaker. Okay, so now we have both components sitting there stirring around. Okay, let's go to the next component. Sodium deoxycholate. Now we don't care about the formula weight because look, we want it as a percent. So that's irrelevant. We don't need it. We want 1%. Remember, 1% weight over volume means 1 gram over 100 mils. But we decided we don't want 100 mils, we want 1,000 mils. So how much do we need? And if we do this arithmetic, we get question mark equals 10 grams. So again, we're going to add that into our beaker. It's all stirring around and around. Now we have 3 of our components. Okay, and we want 0.1% weight over volume SDS. Again, we don't need the formula weight. It is irrelevant. We know that 0.1% means 0.1 grams in 100 mils. But we don't want 100 mils. We want 1,000 mils. So how much do we want? And the answer is that we want 1 gram. Okay, now we have them all stirring around and around. We have maybe a little bit more than 700 mils because we start out with 700, but we've added stuff to it. And then finally, what we would do is we would bring it to a volume of 1 liter. Now, I did ignore, because we're not talking about, let's just say we have a graduated cylinder and we bring it to a volume of 1 liter. Now, I did ignore this issue of the pH. So at some point, we would have to adjust the pH. It would be very unusual. Well, we just wouldn't use tris buffer without bringing the pH down, because when we first dissolve tris buffer, it has a very high pH. So the pH is brought down. Again, that wasn't the topic for this video, but at some point, maybe before we, well, certainly before we bring it to volume. So maybe right here, we would adjust the pH to what we want, which is maybe 7.4 would be pretty typical. So we would adjust the pH to 7.4, and then we would bring it to a final volume of 1 liter. Okay, so that's REPA buffer, and that finishes up this video with calculations for multi-component solutions. So thanks for staying with me on these videos, and good luck making your solutions in your lab.